So next we have Cambridge Quantum Computing, and Tom Benjamin and Krithik Puthalath will tell us about their focus areas.
Okay. Once again, thanks for hanging around during happy hour. We appreciate you taking the time to hear about Cambridge Quantum Computing that we call CQC. I'm Tom Benjamin. I'm with the CQC subsidiary in North America. And Krithik, my colleague, is also with North America and is from our Berkeley office. Cambridge Quantum Computing was a spin out from the University of Cambridge Accelerate program in 2014. Our founder, Ilyas Khan, has strong connections to the University of Cambridge. He was successful in the financial world and in investing, and was one of the co-founders of the company back in 2014. He was also the founding chairman of the Stephen Hawking Foundation, and a real dynamic leader for our company. The company has grown in that time to about 80 people now, about 50 scientists and engineers, based largely in the 4 locations in the United Kingdom: London, Chessington, another location in London, and our science team is basically headquartered near the University of Cambridge. 2 of our colleagues from Cambridge are here today and presented their paper on Monday about the qubit rooting problem and the application of their signature software, the ticket compiler, to that technical challenge. Ross Duncan is the head of the quantum software team, and Silas Dilks presented the paper on Monday if you were here for that early Monday morning session. We're primarily focused on quantum software. We do have one hardware effort that Krithik will tell you more about. As I mentioned, the company started in 2014, but in 2019 we've really expanded rather dramatically by opening offices in Arlington, Virginia, in the Roslyn section just across the river from Georgetown University, and our office in Berkeley, California, as the 2 North America presences. At the same time, in February, we opened an office in Tokyo. One of our investors is the JSR Corporation. Some of you may be familiar with JSR Micro in Sunnyvale that works on photoresist materials and other material science applications. And we have a presence now in Tokyo for that, to support not only our relationship with the investor and their programs, but also to do some business development and outreach. My other colleague that is here is John Pickerel, head of business development. He and I populate the Arlington, Virginia office. And with that, I'll turn it over to Krithik, and he'll tell you more about our technologies.
Can you hear me? Yeah? Good. So thanks, Tom. Thank you guys for staying after so much and listening. I know it's quite late, so I'll keep it pretty short. But we can kind of divide the 2 things that we do in CQC into 2 areas. It's in quantum technologies and quantum computing. And like how Tom said, in quantum technologies, our main focus is in encryption and security, quantum cybersecurity. So we actually have a physical device that we've been working on and developing out in the UK. And I'll talk a little bit more about that in the next slide. And then we have extensive work in quantum computing, namely our efforts in Ticket, which is our quantum software stack and our quantum compiler. Quantum chemistry, we have a product called EUMEN. And then quantum machine learning, we have deep efforts in adversarial circuit learning and circuit learning in general. And then just quite recently, we've published a paper on quantum natural language processing. I think it's one of the first papers on this, headed by Bob Cook at Oxford. Yeah, so our first device, our main device is called IRONBRIDGE, and we kind of revealed this in February at RSA in San Francisco, and it's a 4-qubit photonic device. Many of you probably know of this as a QRNG device, and some of the biggest use cases of this obviously is in post-quantum cryptography, but we're developing a whole community for software developers to use this for many other use cases, such as generation of certificates, IoT device cache entropy generation. Quantum watermarking is a big use case as well. And we're planning to actually ship this out at the end of the year. So we're in active development out in Chessington to build out this device. I can talk a little bit more about the technical details if anyone's interested a little later, but it's quite cool what we do with that. So in quantum computing, Ticket is our flagship product. So Ross and Silas are two experts in Ticket, so they're here if you'd like to know more about what we do with that. But it's essentially one of the leading compilers, and it's been developed for a few years now. And where our extensive hardware portfolio, we've integrated Ticket with many of the leading hardware partners out here. The biggest thing with Ticket, I think, many of you already know the main uses of a quantum compiler, so I don't have to give that spiel, but it has one of the best routing and scheduling protocols, scheduling we're actually working on. But if you want to know more about the benchmarking or the actual performance, you can come by and chat with Ross or Silas. Our other big area is in quantum chemistry. So, we're all well aware that in the NISQ era, the calculations that we can do are quite limited, and many of the hardware groups right now have their own software packages, especially for chemistry. But EUMEN kind of uses a lot of the state-of-the-art algorithms, as well as some things that we've developed in-house at CQC. Namely, we have deep efforts in single electron simulation, as well as there's some noise mitigation and integration in the software as well. There's I think right now you can go online and check out our PyTicket, the PyTicket integration with chemistry as a Jupyter notebook off our website if anyone's interested. And again, this is written on top of our compiler Ticket, so all the optimizations are done through that. So clearly there's a big benefit in the circuits that you're getting out of this. So this is a very brief outline of the simulation process. One of the key things about EUMEN is you can also do some forms of excited state calculations, and we've done this through quantum subspace expansion, QSC. So obviously we use VQE as our standard method to get our ground state calculation, and then use QSC to perform some of the excited state experiments. We actually did this with JSR. This was the original project that we developed this out of, and they turned out to be one of our leading investors as well. So actively looking for more partnerships to work with on EUMEN and quantum chemistry. And we've taken this one step further with NPL. And the whole idea with NPL is how can we improve the accuracy of these quantum chemistry simulations. And so Ross has been working on this along with our chemistry team on how to quantify these errors, how do we reduce them, how do we improve our compiler and some of the algorithms that we're working on. And quantum machine learning is the other area. So we have one of the main scientists in quantum machine learning, Marcello Benedetti, who's probably well known for adversarial quantum circuit learning. And we have numerous papers. A lot of the QML papers that have come out are written by him. I think even in the first day gave a wonderful overview of QML. And again, as we know, a lot of these QML algorithms we can't run on NISQ machines, but circuit learning is one of the toy models and one of the introductory models to QML that we've perfected and are able to run on NISQ hardware. There's numerous papers written by Marcello if you're interested. We've cited one of this. If anyone's interested to learn more, please check out this, the paper listed at the bottom. Finally, we have a small effort in quantum natural language processing. This was very recent. It was a stealth project for a few years, but it was headed by Bob Cook in Oxford, and it's using, obviously, quantum computers and exploring the problem of natural language processing. And the paper's been out in archive for a few weeks now, but it's one of the key areas that we're trying to focus on. I don't think there's a lot of groups who have been involved in QNLP, so it's one of the things that we're very proud of to work on.
just want to summarize, as Silas did in his presentation of the Cubic reading paper, that we are hiring. We've got several open positions in the UK right now. We've got position descriptions at our table outside. I think it will be there for the next 2 days of the NIST conference as well. And all the positions, all the open positions, and many of the papers that we've published and more information about IronBridge are available on the website cambridgequantum.com. Thank you for your time.
Okay, great. Questions?
I was curious about IronBridge and how you're marketing that versus other kind of mathematical post-quantum techniques, and are you getting interest in the QKD approach?
So I think IronBridge, it was originally started out with the idea of exploring QKD, but it's not a QKD device. It's the only device on the market right now that actually uses entanglement and the Bell test to do the certification for non-deterministic entropy generation. We are looking to do more work in QKD, but IronBridge is not that. Yeah.
More questions?
Does your quantum chemistry algorithms outperform classical ones?
Say that once more, sorry?
Does your quantum chemistry stimulators outperform classical ones?
I think in terms of the actual experiments that we've run right now, as we do in the NISC era, we're getting results that we're seeing are comparable to the classical algorithms, and that's kind of the goal now, to make sure everything that we're running is close to that. Yeah.
Question there.
I'm sorry, I still don't fully understand. What is this IronBridge device that you have? Does it connect two parties and allow some secret communication, or it generates a certified randomness? Or
That's right. It's a certified random number generator. That's correct. It uses it's a photonic device, so it uses like a regular laser through SPDC, and we construct entangled pairs of photons, and then we do Bell tests on top of that.
And so it's you say it's a certified randomness by Bell test. It means that you have like so quick measurements that it's like, is it a proper Bell test, or it's just as you assume that there is no communication between the two?
No, it is a proper Bell test, but obviously we're not 100% device independent yet. I think that's the biggest problem. There are some small loopholes as we're building the device at this scale, especially with locality, for example. But for the most part, it does follow that encryption protocol that we know from Bell.
Okay, thanks.
Other questions?
Yeah, I was wondering what you do at your various locations. Like if you do specific parts of your program at specific locations, like say in the US versus the UK versus Tokyo.
All the technical work right now is being done in the UK. The quantum software work is being done with Ross and Silas's team at our office near the University of Cambridge. The office in Chessington is a lab for the engineering and the development work on IronBridge. Business functions and the AI and QML work are being done in London. The offices in Arlington, Virginia, and Berkeley, California, and Tokyo are focused right now on business development and client engagement. But we, again, have been through a pretty rapid growth phase, and will be continuing to grow operations in all those locations.
Do you expect to start like moving some of your like scientific like aspects to, you know, out of the UK at some point, or?
That will really depend on how the client engagements go and how those develop. If the clients are in the US and need close support from our technical team, then we'll certainly meet those needs and requirements. But again, both offices in California, well, all three offices, California, Virginia, and Tokyo, opened formally in February. So we're moving forward.
Thanks.
More questions?
So another question on compiling. So I understand that DKIT essentially works on a like abstract circuit description, and it has a notion of qubit connectivity. But well, while we are in the NISQ era, probably if you want to get optimal results out of running an algorithm on real hardware, you have to take into account further parameters like the varying noise levels of different qubits and crosstalk and these kind of things, which are more hardware specific. Are there plans to extend DKIT in a way that it would be able to take such things into account when compiling?
Yeah, absolutely. I think that's the way that we're going for. Ross is right behind you, so you can get the direct answer from him. Yeah.
So actually, I wanted to ask one more question about IronBridge. So I guess you said it's a quantum random number generator. You also said that the application is post-quantum crypto. And I guess I typically think of post-quantum crypto as something that needs to happen, on my laptop over the classical internet and has to do, complicated things like public key encryption and digital signatures and these sorts of things. So what exactly did you mean by using a random number generator to do these things?
So the PQC algorithms that are kind of approved by NIST, they're classical algorithms, but the biggest vulnerability in that is having a truly non-deterministic entropy source. So the actual device that we're building has these algorithms that are programmed in the FPGAs. And so with the QRNG source, we're able to do a full device that does the encryption.
Okay, so as hardware random number generation that would be then fed into these public key classical algorithms and so on.
That's
what
right,
you
yeah,
mean.
yeah.
Okay, thanks. Okay, so let's continue on. So let's thank Tom and Krithik again.